Lesson 18 in Module 1 is entitled Equations Involving a Variable Expression in the Denominator. So there are two instructional outcomes here. One is to interpret equations like 1 divided by x equals 3 as two separate parts of an equation. The 1 divided by x equals a 3 part, and the part where it defines what x cannot equal, and in this case x cannot equal 0. The second one is to find a solution set for these systems of equations. So lesson 18 is kind of a follow-up to lesson 17, where in lesson 17 we had something like x plus 4 and then x plus 3, and we said what makes it equal 0. And so we would divide this up and say x minus 4 equals 0, so x would equal to 4, and then x plus 3 equals 0, and we would say that x cannot equal to negative 3. So these would be the two things that x cannot equal in that design. Same similar question in this one. It's just we're focusing on the denominator for the most part. So if we looked at question number 1, it says rewrite 10 over x plus 5 as a compound statement. And so we have this notion here where when we look at it, we've got the 10 plus the x plus 5, and really what we want to note is be able to say what x cannot equal. And so we'll take a look at this denominator, and what students will do is they're going to take that denominator, the x plus 5, set it equal to 0. And so then I'll subtract 5 on both sides, and so x cannot equal negative 5. That's the missing part that we're looking for, and that brings up that notion of and. So we have two parts. We have the 10 plus x plus 10 divided by x plus 5, and we have the part that says x cannot equal to negative 5 because it would make the denominator equal to 0, and that's something that we do not want to have happen in this case. So if we looked at exercise number 2, in part A, it says, is it permissible to let x equal 5? So in other words, they're asking, is it okay to say 5 squared minus 25 and do 5 squared minus 9 times 5 minus 4? When they're saying the word permissible, they're really asking the question is, if I put 5 in the denominator, would the denominator go to 0? And so we see the 5 minus 4, that would equal 1. And then you would have 25 minus the 9. And clearly 25 minus the 9 will not equal 0. So is it permissible? The answer would be yes in that perspective, basically because the denominator will not equal 0. So then they ask in part B, is it permissible to let x equal 3 in this particular expression? And that's where we're going to run into a problem, because if we look at this x squared minus 9 part, if I put in 3 squared minus 9, well, 3 squared is 9, and I subtract 9, that whole piece in the denominator is going to go to 0. Well, 0 times anything, where in this case is x minus 4, that's going to equal to 0. So here, is it permissible to let x equal negative 3 in this expression? The answer would have to be no. And then in part C, it says give all the values that are not permissible. So we already know one value that's not permissible, and that was the x cannot equal negative 3. And so we can take the other part, the x minus 4 part, set it equal to 0, solve, and x equals 4. So the other one that cannot be would be 4 in that given scenario. Oh, and we also want to mention, if we are talking about a squared here, and solve the x squared minus the 9 equals 0, if we add 9, you get x squared equals 9. If you square root, you get not only positive 3, but you get negative 3, so we want to add a positive on top of that 3 as well. So another example to take a look at, they say this one here, rewrite the equation into a system of equations, or basically a compound statement for that design. And again, they're really just asking what can x not be in this situation. And so if we write our compound statement, we would just leave the 1 over x equals 3 over x minus 2 alone, write the word and so now if we want this denominator to go to 0, well, all we have to do is place a 0 there, so x cannot equal 0. This one we would actually solve. So on the side we would say x minus 2 equals 0, and note that if x equals 2, then I'm going to have a 0 in this denominator, so x can also not equal 2. In this particular example here, part A, again, we'll do the same idea again. They want us to write the compound statement. And so if we write that compound statement, we'll say that x plus 3 over x minus 2 equals 5 over x minus 2. We'll write the word and. We want to know what x cannot equal. Or in other words, what makes the denominator equal to 0. So if we look at this one, we say x minus 2 equals 0. So x equals 2. And same thing with this one, x minus 2 equals 0. So x minus 2, or if I add 2 on both sides, x would also equal to 2. So the other part of that compound statement would say x cannot equal 2. Now, in addition, the teacher may have the students solve some of these for x as well. But for these particular examples, my focus with you is to help you get a deeper understanding of what the denominator cannot have in it in order to make it equal 0. So if we just looked at a couple, and there are a lot here, exercises 3 through 10, as if you look in your child's manual, you'll note that. So we'll look at some. So if I looked at this one for example, and they gave us 5 over x equals 1, and I want to focus on what can the denominator not be, then I want to be able to say that x cannot equal 0 in this perspective. If the teacher asks the students to solve it, then I could have this 5 over x, I could set it equal to 1 over 1. I could do the cross product to where I get 5 equals 1x, or x, and so I can say that x does equal 5 in that given situation. So perhaps if we looked at another one, let's say this one here, we could say 1 over x minus 5 equals 3. And so the question we're asking first is what cannot be x if I want to avoid 0. So I can doodle on the side, x minus 5 equals 0. So if I add 5 on both sides, then if x equals 5, then I would have a denominator of 0. So we want it to say x cannot equal 5. So if I wanted to solve the proportion itself, I could say 1 over x minus 5, set that equal to 3 over 1, and do the cross product. So I would end up with 3 times x minus 5. We'll do the distributive property there in a minute. And then 1 times 1 is 1. So if we distribute, you get 3x minus 15 equals 1. I can add 15 on both sides. And so 3x is equal to 16. I can divide that by 3, and x will simply equal 16 over 3 as an actual solution. So here, this is what gives us a solution, and right here, this is what x cannot equal if we want the equation to hold true. So again, there are several others. I won't work through them all. But here you have the 2 over x equals the 3 over the x minus 4. Same thing here, the x over x plus 6 equals the negative 6 over x plus 6. The x over 3 equal over the x plus 2 equals 0. The x plus 3 over the x plus 3 equals 5. And the x plus 3 over x plus 3 equals 1. And so these were done in class as well by the students. But you get an idea. Our ultimate goal is to do two things. And those two things is, one, to find out what x cannot equal, and then to go in and solve to find out what x can equal in this particular lesson.